And we're recording now. So for those folks who aren't able to join us live, they can always watch this later. And if you are in the future now, please let us know. What's it like? Do we have flying cars? Are there flying cars where you are? If there are, come pick me up because I'd like to try flying in a car. So what we're going to do first is take a look at that problem set. And I do want to spend some time on this, not just as a what was difficult. I'm going to put us into breakout rooms, and I'm not going to use the team breakout rooms. I'm just going to split us up into breakout rooms. We'll do 3 rooms. And we're going to split up, so make sure you have the agenda, but also make sure you've got your problem set handy. And what I'd like to do is start going through problem by problem and kind of come to a consensus, see if you guys can all come to a consensus on particular problems. If you run into a situation where you're like, oh, we disagree on this, then focus your attention on it. But if you're going through it and you're like, yep, we agree on these, then just move past that. There's no reason to literally look at every single problem, every single part. Just talk them through for starters, and then if you have to drill down, drill down. So we're going to do that for the first 20 minutes or so. I'll pop into each room and kind of see how things are going, but really that'll be what we're going to do for the first 20 minutes or so, and then we'll come back together. Sound good? And the reason I'm doing this now is because I'm going to be able to get this graded, the problem set's graded, but probably not until like Saturday. And I want to make sure you guys are 100% and comfortable and clear on this problem set before you skedaddle. Uh-oh, did we lose somebody? Oh, I don't know. Pictures were moving around on my screen. I don't know what happened.
I think we lost Austin.
Way to go, Austin, because he had computer problems again.
Figures.
It's probably the dog that did it.
Like he has more computer problems at Abby's house.
Yeah, it's, I wonder, was it a connection there maybe? I don't know. Okay, so I'm going to put you guys in a room, and then I'll stuff Austin in another room when he joins us again. So work through the problems, but talk through them first. Don't do the just, here's what I did, because that's not going to be helpful. I want you to talk through the solutions first, and then we'll get back together. I'll pop in. So, doodle-doo. And I'm going to pause the recording because it's not exciting to watch me sit here and drink or whatever it is that you do. So, okay, now that we've had a chance to take a look at least some of the problem set, if not all of them, I wanted to touch on a couple of really important ideas, big ideas that popped up in some of the teams and some of the breakout rooms, but not necessarily all of them. Number one, and I mentioned this, I think, in a couple of the breakout rooms, is this idea that you are using, and you will be using for the exam, certainly, you're using an incredibly powerful tool to do mathematics. Don't hamstring yourself. Hamstring yourself? What's the word I'm looking for? Don't hobble yourself. There we go. That's better. Don't hobble yourself. Use the tool. If I ask you to solve a problem using a particular method, there is nothing stopping you from using Maple to solve it and say, oh, I know what the answer is, so I know my answer is correct. So please, please make use of that tool. This class is not designed to be we're going to learn this particular method and now you're going to do 50 problems to practice that one analytic method. You're to the point now where either you're learning the methods as you go or you're creating materials for yourself that you can refer back to later. Right? So later on in the course, for example, we're going to use a different version of the lucky guess method. Later on in the course, we're going to reuse the integration factor method. And both of those are going to pop back in again. And if you don't remember, it's been a while, I don't remember how to do those. You need to be able to quickly figure out how to do those based on your notes, based on the materials that you've created for the class and the materials that are available to you. But you should always be able to use Maple to solve a differential equation. And if you can't solve it or make sense of it, solving it just with a D-solve, remember you can always solve it numerically with Euler's method. right? So you can always make predictions based on things. So that was number one. Make sure you're using the tools properly. The second thing that I wanted to touch on didn't, as far as I know, didn't come up in all the groups, but I did want to talk about it. I'm sharing my screen where this is problem number 2. And if you remember, problem number 2 was try to solve this non-homogeneous differential equation. And if I remember correctly, let me roll back my screen here because I don't remember exactly what the wording is. It says using any analytic method. So for those of you who jumped right into it and went, I'm just going to use the integrating factor method, then you probably had no trouble with it other than the fact that you had to do some manipulation. It's a bit of a pain in the tuchus. Those of you who decided to try the lucky guess method, you may have run into a problem. So the first step in the lucky guess method, remember, is find that solution for the homogeneous part of the differential equation. And by this point in time, if I gave you that, you should be able to solve that in your sleep. You've seen enough of those where you're like, oh, it's just a constant times y. I know what that looks like as a solution. But then when you decided to go ahead and do the lucky guess method, you manipulate things and you say, well, based on what I've got written here, the lucky guess that I would try would be something like a constant times e to the t over 2 power, right? Because that's what it's got to turn out to be with the lucky guess. And so you take the derivative and you say, okay, now I'm ready, and you sub it into the differential equation. So you substitute the derivative here minus 1/2 of the original lucky guess, and it's got to be equal to 4e to the t over 2. And what you find is you have 1/2 a t e to the t over 2 minus 1/2 a e to the t over 2. And those two things go bye-bye. So your entire solution process is thwarted. In other words, there is no solution. There is no value of A that can ever make this true. This is a failed guess. And so this is what it looks like when you get to the end of the lucky guess method and you weren't so lucky. This means that A e to the t over 2 is not lucky. It doesn't work. No matter what you do, it will never work. And so you're faced with a conundrum. And the conundrum is either you guess again, and you might think, well, I don't know what I would guess other than that. So I don't know what to do. The other possible solution is, okay, I'm just going to pull out the big guns and use the integrating factor method, which you could have done from the beginning. The third possibility is you hop on Maple and you say, hey, Maple, what's the solution for this? And can I read something into that? And so I really want to pull up Maple so you can see kind of what that looks like when we solve it. And it's going to take a while for my Maple to pop up. So in the meantime, how many people started off with I'm going to try this using the lucky guess method? How many people started with the lucky guess method? A couple of people. And when you ran into that, where 0 equals something and that can't possibly be true, what did you do? Did you just abandon ship and jump over to the integrating factor method? This is the audience participation portion of tonight's program. What sayest thou?
Just gave up.
You just gave up. You're like, fuck it, I'll never get it. You walked out of the room. You burned your computer. No. No, of course not. But, sometimes walking away from a problem is a perfectly valid solution strategy, because the way you're thinking right now may not be the way you're thinking in an hour after you've gone for a walk, or it may not be how you're thinking after you've had a little bit of sugar water in your system to replenish some of the glucose that you're burning, right? Don't discount the power of changing your point of view with something to eat, something to drink, soft drinks only, or going for a walk, or just talking to somebody about something completely unrelated, or going to sleep, taking a nap. One of my favorite solution strategies in graduate school, when problems got really, really thick and I was like working for 4 hours on a problem, and I get to a point and I'm like, I have no idea what to do. I'd be so tired. I would literally go in the other room, put my head on a pillow, and sometimes not even sleep, just kind of rest for 15, 20 minutes. Sometimes I'd fall asleep, take an hour nap. but I'd wake back up and I'd sit back down and be like, oh, yeah, I didn't try this other thing. And it just pops in your head because you literally give your brain a chance to kind of ponder a little bit in the background. The process is working in the background. So I did want to show, let me see if I can pull this up. That's a little too big here. Let me change the share on this. Okay, so you're seeing my Maple screen. So with DE tools, and I don't know why, my Maple, every time I do that, I'm just waiting. It's like it really has to think about what DE tools involves. There we go. Okay, so I'm going to do desolve, and we're going to type in our differential equation. So this is y of t with respect to t equals y of t over 2. Is it plus? Yeah, plus 4 times exp t over 2. T over 2? He said t over 2? Come on. And close that out. And so give Maple a second, and we see something that may be helpful to us. In other words, you can see right there, this term, the constant times e to the t over 2, I recognize that. That's my homogeneous part of the solution, right? So that's the part that I knew to begin with, constant times e to the t over 2. The part that I'm having trouble with on the lucky guess is coming from this term times e to the t over 2. But notice, it's not just a number times e to the t over 2. It's a number times t times e to the t over 2. You're like, huh. So maybe my lucky guess should look like that. And sure enough, if you try a lucky guess that looks like that, it does work. So let me switch that over. I'm not going to go through the entire process, but if we kind of cross this out and say, well, that didn't work, so let's try another lucky guess. With the help of Maple, we can try a guess that looks like this. Y of t equals a times t times e to the t over 2. It's still got the e to the t over 2, but now we're adding that factor of t in there. And by the way, what we just did, throw a t in there, becomes actually a valid method for, oh, that guess didn't work. Multiply it by t and try it again. That actually works almost every time that your original guess doesn't work. It's crazy, but it's true. And it has, we'll see later on what it has to do with. But if that's the guess, notice it's a little bit tricky, the derivative of this thing, because it's a product rule situation. So we're going to have multiple terms. This isn't just a one-term derivative. It'll be a times e to the t over 2. That's times the derivative of t. Plus a times 1/2 t e to the t over 2. So notice we have one term that doesn't have a t in it, and then another term that does have a t in it. So when we sub this thing back in, sub that guy and this guy in for our function and its derivative, we wind up with dy dt, just a reminder, equals, what was it? Y over 2 plus 4e to the t over 2. That's our original equation. So when we sub this thing in, our derivative is all of this right here. A e to the t over 2 plus a times 1/2 times t times e to the t over 2. The other side is just our guess, this thing right here, 1/2 times a times t times e to the t over 2 plus 4e to the t over 2. Now notice what happens. You might think, oh my God, it's a mess. But notice on this side we have a times 1/2 times t times e to the t over 2. But we have the same thing here. So these two terms, just like they did with our previous guess, those cancel each other out and go away. But we still have a term left that has an a in it. And this is the saving grace of our guess when we throw a t in as an extra factor in there. So the derivative creates an extra term that does the canceling for us. So now we have a e to the t over 2 equals 4 e to the t over 2, which means a must be equal to 4. And so our lucky guess works, and we wind up with 4t e to the t over 2. And so our overall solution at the very end is our homogeneous part, which is c e to the t times e to the t over 2, plus our particular guess, which was 4 times t times e to the t over 2, which is exactly what Maple gives us, right? So you might look at this and go, oh, I would never have known to guess that. That's okay. Once you see it, once you see one example where you're like, oh, so we can just change the guess like that, and if it works, run with it. That absolutely is 100% fine. Now, those of you who did the, that's what I'm looking for, the integrating factor method, how does this compare to the amount of work you had to do for the integrating factor method?
This one's way too much.
This way is too much?
Yeah.
Oh, so the integrating factor method was quicker?
Yeah.
Okay. And you know what? There's nothing I can say that will change the diehard integrating factor fans to switch them over to like, oh, I should use the lucky guess method. I completely accept that. I've gone are the days when I tried to evangelize for the lucky guess. But suffice it to say, both methods lead you to the correct answer, right? Now, you might look at it and go, well, I don't want to use that method anymore. But, you know, you may run into a situation where that would work. Somebody's getting $30,000 in scholarships and grants and financial aid to go to Hope College? Or is it Bro Hope College? Matthew, where's Bro Hope College? Is that like somewhere like in Canada or California where you can go to like Bro Hope College or what?
It's just the south of Maine a little bit.
South of Maine,
Like,
Bro Hope.
yeah, just a little bit. Like
What do
an
you
hour.
mean it's awkward? It's not awkward. Congratulations, dude. That's awesome. That's really, really cool. But it is awkward that you wrote Bro Hope College. So I'll take your awkward to mean that. But otherwise, knock it out of the park. Way to go. And I agree with you, Stephen. I would like $30,000 too. One day, maybe if I work for 3 or 4 years, I'll be able to get $30,000.
My goal in life is to one day be able to buy $1 million.
To buy $1 million. So if somebody like writes $1 million on a piece of paper and then sells it to you,
yeah,
for $1, that'd be kind of cool.
That's the big plan. Okay,
well, I'm going to stop sharing my window, and Matthew's going to let us in on some of that Bro Hope money. You know what I'm saying? Hundreds. Yeah. Oh, yeah. Well, congratulations on that, and welcome back, Austin. So what I'd like to do now is number 1, number 2, and number 3, those problems are all problems that you can use Maple to get the solution for. So there's no question you'll have the right answer if your answer looks like what Maple's does, right? You're shaking your head no, Matthew, or not about this, something else? Well, bro, I hope that you hang in there for the rest of this problem set. So what I'd like to do is turn our attention to numbers 4, 5, 6, and 7. And so there's 4 problems, and they're all kind of story problem-ish. But specifically, I would like to have you guys in breakout rooms in your teams. So we'll go back to the teams. I'd like to have you guys go back to the teams to work on those problems. And so I'm going to have I'm going to have to type, and I can't type and talk at the same time. So if somebody would like to claim for their team one of the problems to talk about, because you're going to not only come up with a solution, but you're going to present that solution to everybody. So 4, 5, 6, and 7, those 4 problems, you got to choose one of them for your team. So speak up
Team T
now.
claims 4.
I speak for 5.
Guess we'll take 6.
Okay, so everybody is clear on everybody is clear on what their team is doing. So I got to finish assigning these. It's just going to take me a second to assign the rooms. It's kind of a tedious process here. So Austin, Paul, Wyatt's not here, and Quentin's here. Okay, and then we're going to assign for that one. Matt, Stephen, and John. And then Bryce and Emma. Okay, so I'm going to open up the rooms. You guys know what problems you're working on. The game plan here is you're going to be presenting a solution. I'm only going to give you about 10 minutes so that we get all of these presented. Which one is the problem that's not being looked at?
I think 7.
Number 7? Okay. So number 7, it's dead to us. Or maybe we'll all look at it together when we get back. So I'm going to open up the rooms. Go work with your teammates on your chosen problem and prepare yourselves. And I'm going to hit pause on the recording. Okay, so now that we're recording, let's take a look at problem number 4.
All right, we had problem number 4. I wanted to repeat myself for all the future car flyers.
That's right.
Can you see
So
my
far,
screen
nobody's come back in time to tell me about the future. So I assume time
It doesn't
travel hasn't
exist.
been invented yet.
I think that
It's
just means
actually,
that
this is actually one of the strongest pieces of evidence for the fact that time travel will never happen, like traveling backwards in time will never happen, because if it will happen, then somebody would come back in time, which is why sometimes I like to start the first day of a class. I walk into the classroom and go, see, I told you I'd do it. And then I walk back out of the class. And then I come back in and I act like I've never seen these people before. I introduce myself, blah, 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 blah. The very last day of class, the last thing that I would say is, okay, now that you're all done with your final exam, I just want you to know I've been working on time travel. And someday in the future, I promise I will come back and show you that I've found a way to do time travel. I did that once, completely blew the minds of 2 students who were still in the room at the time. But I thought it was very funny, but one person was like, that's really lame. And I said, come on, how many people do you know that can wait an entire semester to pull off a joke? So that's a long time to wait for payoff. But anyways, sorry. Over to you, team.
number 4. It
Over
says
to
the
you.
host has disabled attendee screen sharing.
Oh,
You know,
you're so needy. Okay.
all right. I'm sorry.
Okay.
I'm trying to work on that.
Go for it.
Okay. Number 4. That sounded like one of those top 10 videos.
Number 4.
Okay. Number 4 of the top 7 most problems on this worksheet.
Problem set.
All right. So for some backstory, we have a tank, and this tank has some salt water going in 2 pipes. And then the same salt water, well, not the same salt water, and water from the tank is being drained later. Yeah, that's about it. It's a 320-liter tank. It starts off with a bit of salt and a bit of water in there already, and we want to model some stuff. So the question was, what was the question? We're supposed to figure out the amount of salt in the tank when the tank reaches its capacity. And so that's what we set about doing. We started off with our input minus outputs equation. And so for our input, we took the one input, and then we just added it to the other input. And then we got this for our net input. And for our output, we said we only have one output, so we just made that our output. And then
Now, to be clear, you're talking about inputs and outputs, but kilograms per minute is not the same units as liters per minute. So you're comparing.
That is correct.
So you're comparing a kilograms per minute would be, I guess, it's the dsdt, comparing that to the flow rate out of the liquid, which is a different thing.
I'm sorry, what?
I'm just pointing out the fact that your 3.81376 kilograms per minute, that is the input of salt per unit time. You can't directly compare that to 10.34 liters per minute. That's a completely different quantity.
Well, you are correct. And so what we did is we did some fancy schmancy stuff.
Cool.
And then we just shoved a bunch of numbers and variables and things. And we got our output into kilograms per minute.
Can you talk real quick about the denominator on that? Where does that
The
denominator come from?
denominator, this is the denominator. It's right there. And we said, hey, you know, we already have some bit of liters of water in there, right? And also it is increasing at a rate of this right here. So this is the difference between the input and output rate. So the overall.
And it's
difference
literally the difference in the flow rates of liquid.
Yeah, not salt, just flow.
Yep.
So we got 4.213 is our total difference in like overall. And we said, well, that's going to change over time. And so we slapped a little t on the end and added it to our original amount of 225 liters.
And I'm gonna pepper you with one more question. The
Sounds good.
4.213 has units of what? 4.213.
That should have units of, altogether it
Liters.
has units of liters, right? So it should have units of liters just straight up, right? Because we're adding it to liters in general.
Nope, you're not adding 4.213 to it. You're adding 4.213 times t,
So it should be liters per second, the times the seconds.
minute. Yep.
Minute, you're right. Liters per time unit.
Yes.
And
And
then
that's
that
important,
is-
right? And so by finding
Is
that
important.
difference in the flow rates, what you've essentially done is said every minute that goes by, the tank is going to have a net gain of 4.213 liters. And
That's
so
a
you
much
want to,
easier way of thinking about it than what I had.
and that's okay. That I want people to see this, and that's actually I think the hardest part of this problem is recognizing that that denominator is a more complicated function in and of itself, because you're not keeping the level of liquid the same in the tank. It's going up. Which, when you think about it in real life, you'd have to have things just like perfect to have the flow rate from two pipes completely matched by the flow rate out of one pipe. It would have to be perfect. And usually it's a little off. One direction is bigger than the other. So
Because my thought process was, oh, I need a linear function, and so I better have a linear function. And that was it.
but linear because it's going up at a constant flow rate, right?
Yeah. Linear because the flow is constant over here. We need to slap some time on that, and then plus initial state.
Yep.
So anyway,
Cool.
this is our outflow. That's what we got. And then we said we want a full-on equation. And so that's what we did. We named it D for differential equation, I guess. Yeah. And so we declared D, and then we said, hey, we should solve D. So that's what we did.
And notice
And we,
notice that DE, the way he named it, he named the entire equation. And so he can refer back to that entire equation as one full unit. And that's a handy thing to be able to throw that in the DSolve. And it's not a crazy differential equation. Sometimes they get crazy, and which is where the original phrase, the differential equation is nuts. That's what they used to say. And then they shortened it down to just DE is nuts. And then they shortened it even further from there, and popular culture took it from there. You may be familiar with that phrase. But anyways, continue.
So anyway, so we solved our D, and we got this, which looks gross, and that's because it is. And then we thought it would be much handy if we could just refer to this as P of T. And so that's what we did. We declared the whole, what's it called? I'm blanking on the technical terms. Particular solution? Yeah. We got our particular solution. We called it P of T. And now now we need to figure out when we reach our capacity, which would be 320 liters, because that's how much our tank can hold.
Okay.
So we did some more math, and we said, we got back our friend, the 4.213 times time, to figure out how much fluid, how much time will pass when the fluid reaches the top of the tank. And then we solved for T, and we said, hey, we have 22 seconds, well, 22 and a half seconds until that, not seconds. What is this, minutes? Is that the original time?
Oh, it's always good to keep an eye on the units. Yep, it's minutes.
22 and a half minutes. And then the question then remained was how much salt was in the tank after 22 and a half minutes. So we just plugged it back into our particular solution, and we figured out that it is in fact about 88 kilograms. Yeah, 89 kilograms. when it reaches its maximum.
So how do we feel about that, gang? Anybody have any questions for him on that? How about other teams? Do you agree, disagree on that solution? You can unmute your mics real quick.
I agree with it. What I got.
Cool. Others?
I agree. But I'm on his team. My only question is so I when I did it, I used my calculator and instead of like how he used Maple for everything, and I got like slightly different numbers, and I ended up getting like a whole different, like I did the same exact method, but it wasn't like crazy off, but it was off by like a good couple. So would I, like in this sense, okay, if I would have turned that in, would I have gotten marked down even though I did the right method and everything, I did it all fine, but because I rounded and didn't take it right from Maple like he did, would that be?
So you're asking two really good questions. The first one is, when do we round?
Yeah.
And the second question is, what kind of penalty is there if I kind of
Make a rounding error, yeah.
make a rounding error? So the first question is only at the end. The answer to that question is only ever at the end.
Okay.
You should never round prior to the end. Because if you think about this as like a string of calculations, and it's kind of nice in the Maple document, you can see that it's really just a series of calculations. And at no point did we have to round. We could have. And so when Stephen was showing us his answer for, this plus this equals a number, he could have referred back to that output in the next calculation. He could have said, take this number from line 3 up there and do this with it, right? And you wouldn't have to round. You wouldn't lose any decimal points or decimal places.
Yeah.
So the answer is never round until the end. And the second question is a good one. You'll notice on there I didn't say what's the amount of salt in the tank out to 3 decimal places. But on the exam, I will say something like out to 3 decimal places. And if your answer is, if you've rounded too much too soon and you lose it's technically losing precision as a result of the rounding, then you will get dinged if it's not accurate out to 3 decimal places.
Okay.
So it's a matter of precision there. So
Okay.
yeah, but I'm not gonna knock off half the points for the problem. I might ding you a point for the problem just for precision. But yeah. And just as a side note, you have Maple. You don't need a calculator. You might use a calculator because it's easier or because you know how to do it on your calculator, but there is nothing stopping you from using Maple to do all your computations. And honestly, since you're going to be turning in the Maple sheet, you want me to see your calculations. You don't want to go, and I feel like the answer to this is 2.6382. It's like, well, shit, where did that number come from? How do you feel that way? Where'd that come from?
Okay. I didn't know. Because,
Great question. Very good question. Yeah. Okay, how about number 5? Who had number 5?
Yes, that was us. Let me share screen here.
P and Q. Mind your P's and Q's. Here comes Team Diff.
Okay, so we had the dp, the rate of change of p over dp over t equals the growth dimension plus the growth of the deposit.
And so this is for the first part when the professor is adding money to the account and it's doing nothing.
Yeah, I split up the 2 parts. Yeah.
That's cool.
So that was 0.05p plus 5200.
Okay.
And from there I found the homogeneous equation, which was C equals CE to the 0.05t. And then I found a particular solution, which was dp over dt minus 0.05p equals 5200.
Cool.
So then I guessed that the particular one was equal to a, and the derivative of that was 0. So then let's see, what did I do here?
Yep. You're plugging it back in to figure out what the A must be equal to. Nice.
And then I found that A equals minus 104,000.
Okay.
So then I made up the general solution.
Yep.
Or the general solution. And plugged in the original condition, initial condition,
Yep.
which was 0. And so then I found the C was 104,000.
Cool.
And so that gave me the particular solution for PFT.
Okay. So you got your particular solution. Then your next step was to do what?
Put in the 25 years to see how much money you get.
So that's going to be the amount of money that's sitting in the account the moment this person retires.
Yeah. And that turned out to be 258,000.
So, I mean, it sounds like a lot of money. You're like, damn, he's set. And then part 2, we're going to find out how set is this person.
Yeah. And then part 2, the rate of change was 0.05p minus the amount of money took out is 41,000.
So where's the 41,600 come from? I agree with you, but the units are important here.
Hang on a minute. Oh, that's the 8. Wait. Oh yeah, that's the 800 per week.
So 800 per week.
And then times it by 52.
Times 52 weeks. So, yeah.
So notice that little piece of information is super important. The units for this matter a great deal. So
Okay.
just maybe make a note on the next line and say, note the 41,600 is $800 a month times 52 months a year, right? And so this is just so that when you go back and look at it later and like, shit, where did the 41,600 come from? So that's important. So I'm going to kind of follow along and say, so we get a general solution. This is for part B, where he's actually withdrawing, but still earning interest, right? So there's still money in the account. That part is earning interest, but along the way, he's also withdrawing. And so there's going to be earned interest, but withdrawing. And if it turns out that earned interest is coming slower than the withdrawal, which, big surprise, it is, then this person's going to run out of money. And by the way, this is at the heart of, if you've ever heard of like trust funds and endowments and fancy stuff that rich people have because they have more money than they know what to do with. The only way a trust fund works is if you're not withdrawing so much that it starts to decrease the balance. If the balance is able to remain stable with interest balancing out the withdrawal, then you have a stable trust fund or a stable endowment for organizations. So this is like financial planning, is super important in financial planning. So you go through the process, you find a particular solution for the withdrawal equation, and you find out that, I'm going to scoot down here. You say, okay, so when does the money run out? He says, well, whenever the amount in the account is equal to 0. And so take it from there. The money runs out when PFT equals 0.
So then I set 0 equal to this function, which was the, I don't remember where I got that from. It was somewhere.
That's your particular solution. Yep.
Oh yeah. Okay, so then I just did some calculations and figured out, I just solved T pretty much.
Yep.
And T was 7.458 years.
Now, I don't know about you, but when I saw that, the first time I did this calculation, and I saw that, oh, he's going to have $258,000 in the account, I'm like, oh, he's set for a while.
Not very long.
He's set for less than 7.5 years. So that retirement that he built for 25 years lasts him 7.5 years. Now, if this person retires when they're, I don't know, in their mid-60s, 7.5 years doesn't take them very far. So this is the kind of the interesting object lesson here. What's your retirement plan? Do you have one? Have you ever thought about it? What about you, Paul? Have you thought about retirement?
I have not, no.
No. He's like, I haven't even thought about getting a job. What are you talking about? So this is one of those moments where you realize that you can save for 25 years and then blow through that money. And by the way, $800 a week, when you think about like rent and food and hanging out with your pals, playing bridge and complaining about your grandchildren, I don't know, whatever people do when they're retired, that $800, that's not a lot of money per week. It really isn't. It sounds like it to you may sound like a lot, but if your mortgage is, $1,000 a month, then there's $250 right there. And you're like, oh, I don't know, this is pretty extreme. So consider it as a challenge. If you had to decide what you would do for retirement. And based on your age, based on what you plan to do, how much would you start putting aside on a weekly basis? How much could you save if you put out $10 a week? If you set aside $10 a week, how much could you save by the time you're 65? You might really blow your mind if you do this calculation. Really blow your mind. Or maybe you make yourself really sad. I don't know, depending. For me, it'd probably make me really sad because 65 is not that far away. But oh well. Okay, so any questions on that one? The solution strategy, the approach? Any questions on that? Paul, you did such a thorough job. The only thing that I would say is nowhere in the problem does it explicitly say, thou shalt use the lucky guess method and no other method. I never once said you can't use Maple. So instead of doing the lucky guess method, which by the way, good practice, good on you for doing it, you could have just said desolve and then typed it in and got the solution that way. And that's okay too.
I didn't realize that until later.
Totally fine. Just be aware of that on the exam. When I say I want you to use the integrating factor method, I want to see the integrating factor method. But if I don't give you instructions on what method to use whichever method will get you the solution fastest, right? Or if you're just like showing off, you can do that too.
I think on the top of the thing it said show all your work. So
yeah, and your work on a Maple document can be desolve the equation. I typed it in with the initial condition. There's my solution. That is perfectly acceptable as work. Totally acceptable as work. Okay, number 6. We ready for number 6?
Real quick.
Oh yeah, sure.
This isn't for that one, but on that note,
Sure.
For number 3, you said, show all your work and the integrating factor technique. But like, if we honestly just did desolve to it, is that the same idea or no?
No. Showing the work for the integrating factor method is the kind of stuff that Paul was showing, like step. I mean, you can do the desolve and get the solution, but that's kind of like saying, if I give you 2 3-digit numbers and I ask you to multiply them, and I say, show your work, I want to see the by hand calculation, I'd expect to see one number written, another number written.
I just wanted to make sure that was all, because if you did allow it, I was going to stop. But okay.
No. When it's time for me to, when I'm asking you for the integrating factor method, I want to see the work. I want to see, I manipulated it this way. I calculated my integrating factor method is my integrating factor is this. Then I multiply it through and I did this. Yeah. Okay. So notice, I'm not asking you to do tons of these, but I just wanted clarification. That was
absolutely.
Absolutely. And by the way, on the exam, because it's a little high stakes, if you get to a point and you're like, can I just do this in Maple? And you're not sure, don't say anything. Just be quiet. Don't ask. Of course, I'm joking. Send me an email. Worst case scenario, I say, oh yeah, I want you to do the integrating factor method there or whatever. Like worst case, I say, oh yeah, you got to do it by hand. Best case, I'll go, oh no, I didn't say, so you're free to use whatever method you want. All right. The other, and I'll put this out there as just a cautionary tale. I've had people do work on Maple and they type in the equation wrong. They like put the wrong number in the wrong place, or they use the wrong initial condition and they're off by one number. What does that do to their answer? I'll let you think about that for a moment. Yeah, it's totally wrong. And so here's the trouble. If you have only one method to solve your problem and you don't double check it with another method, you have no way of knowing if you screwed up, other than going back through your work with a fine-tooth comb and looking for mistakes, which, by the way, I don't know about you, but I am always the last person to spot mistakes in my work, right? Because I know I did it, and so I must have done it correctly, right? So just keep that in mind. You have multiple methods for being able to do this work. Use them. Even if you type it in, it's not a bad idea to take the 2 minutes that it takes to solve the equation by hand and say, oh, I got something different. Let me go back and double check. Right? Having multiple methods really is an important way of verifying. So Okay, number 6.
I will share my screen. Okay, so starting off number 6, the problem says, suppose water flows into a lake at a constant rate of R, and that the water also evaporates from the lake at a rate proportional to the volume itself. So first setting up the problem, we just set up the original differential equation as dv over dt. And then our R, our rate as which the water flows in, we left it by itself. And then as it evaporates, it's the volume times a constant. So our evaporation would just be a constant. It's kind of how we thought about it.
Okay. And so can you help me understand what would the units be for each of the terms in your differential equation?
It would be, what is it?
Because you know I'm going to ask a question like this on the exam.
It would be a rate of water, or it'd be like a unit of water over time.
So unit of water meaning what? What would the units be? What does V stand for?
Volume.
So cubic meters or gallons or whatever you're measuring your volume in.
Okay.
Yep. So each term's got to be that. So that means the R has to have what units?
Volume over time.
Bing! And it is a rate. As promised in the equation, it's a rate. And how about the K? What would the K have to have for units?
1 over time.
You got it. So being able to create the equation is important, but also identify what each one of those parameters would have to have. And they're not the same units. R has different units than K. And that's important for being able to interpret our answers. Okay, so we got A, we got our equation. Now what?
Well, is it not right? Because ours.
Oh, no, it's perfect. No, that's great.
Okay.
That's 100% correct. Absolutely.
Okay, perfect. From there for B.
Actually, one more thing. Can you remind everybody, just because I know some people might want to know this, how did you get the inline equals?
Yeah, it's it's Alt Enter.
Alt Enter. Or sorry, if you're on a Mac, I think it's Command Enter. I think. Or no, it's Option or Control. I don't know. Mac people, you'll figure it out. But it's one of those, and so you can get inline equals.
Okay.
That's useful. Sorry. Anyways, go ahead.
Nope, you're fine. And then for B, it says using your differential equation from part A, along with the presumption that the lake starts off empty to find the solution. So I just used dsolve, noting that our initial condition is VO equals 0.
So starts off empty, got translated into T equals 0, V equals 0. Nice work.
And then it gave us this bad boy right here. And then for C, we had to find the equilibrium solution from our differential equation up here. So then we just set 0 for our on the left side equal to R negative KV, and then solve for V, which that actually should be uppercase.
That's okay.
Yep. And then this was our equilibrium solution.
And remember, both R and K are numbers, they're parameters,
yep.
Right? And because we know what the units would be, R is in terms of volume over time, and K is in terms of 1 over time. And when you do that division, you're left with just volume units.
For like on the exam, would you want us to show our units?
I'll ask you if it's part of the question, but otherwise, no. What you did is perfect.
All right. And then for D, it was a little we were a tad confused by the term. What does the sign of the derivative of this tell us?
Yeah.
So how we thought about originally was our VEQ is equal to this. So our equilibrium solution is VEQ. It's kind of how I read the problem.
Sure. Yep.
So then we plugged VEQ, this guy, into our original equation.
Yep.
So,
and the original equation is F of V, not F prime of V.
Yeah,
That's F of V.
So we did that, but before we could even take the derivative, it ended up canceling out to 0 anyway, so we didn't ever actually have to take the derivative. So then I just said this tells us that the equilibrium solution, oh, this is not making sense. So basically at the equilibrium solution, there will be no change at all.
So
I don't know if that makes sense,
absolutely,
but-
if you start off at the equilibrium solution,
Yeah.
it doesn't change. The question is not if you start off there. It's basically asking what happens if you're right around the equilibrium solution. Does it head towards the equilibrium solution, or does it head away from the equilibrium solution? It's getting at this idea of not f of v, but f prime of v. So I'm with you 100% all the way to D, and then you're trying to substitute the equilibrium solution into f of v. I'm saying no, you're going to substitute it into f prime of v.
Okay, so you would
Go back to the very beginning,
Okay.
f of v is the right-hand side of that thing, r minus k times v. Now take the derivative of that with respect to t, with respect to, I guess, v, if you want
Wouldn't
to say
that just be this?
No, no. That's the solution. That's integrating. That's going the other direction.
Oh, I don't know. Oh, just taking the derivative of this?
Mm-hmm.
Oh, okay. Shoot.
And so the trouble that we run into is I didn't say derivative with respect to what, but the only thing that we're taking derivatives of is with respect to time, right? So can you take the derivative of your original right-hand side? And remember that v is a function itself of time.
Not liking that answer.
Yeah.
Not liking that.
It's so what you're seeing there is Maple saying, okay, it's whatever you get when you take the negative derivative of k times the velocity, the derivative of that thing. Now, think about what this means. This is saying k, which we know is a constant, and we know it's a positive value because we've built it into the original differential equation as being a positive value. K times the derivative of the velocity, the rate of change of the velocity. But take a look at the sign that's sitting in front of the K.
Oh, it'll go negative, or it'll approach 0.
Yeah, so this is telling you the negative sign of that derivative tells us that all solutions are headed towards the equilibrium. And so it's what we would call a stable solution, right? Which is exactly what you'd expect. It's going to keep filling up with water until the rate of filling and the rate of evaporation kind of match each other, right? And it's going to approach that stable equilibrium solution over time. It's a little tricky. The problem's a little tricky, but not up until D. Everything up until D, not terribly tricky. It's just the interpretation stage, making sense of that last little bit. How are people feeling about number 6?
Can you go over D just one more time?
Sure.
Like you lost me.
That's okay. So here, let me steal the screen share here. And let me put up where's my document? There it is. So part D says, what do we know about f prime of the equilibrium solution? And so that means we have to figure out what is f prime of that. The equilibrium solution you found was, what was it, k over, or v over r? No, what was it? V equals r over k, right? Is that what it was?
Yeah.
Okay, so we need to figure out what is f prime. And if you remember, f of v was equal to r minus k times v, and that's v of t. And so if we take the derivative of this with respect to time, f prime of v is, this thing is just 0, that goes away, it's a constant, minus k times whatever the rate of change of v of t is. Now, you know what V is, and you know what the equilibrium solution is. And so you could, if you wanted to, go through the process of subbing that in. But really, this is telling us the sign of that derivative right there is telling us that the rate of change of the rate of change, because this whole thing is equal to dv dt. So the rate of change of the rate of change is negative. This thing is, if you want to think of it, concave down. It's heading towards a solution. If you think about your equilibrium solution up here, you know that solutions start off somewhere down here, v of 0, 0, and it's going to wind up being like this. It's concave down, but headed towards the equilibrium solution. Negative implies concave down. So you didn't have to do a whole lot of math other than make sense of the concept of, if I'm taking a look at the derivative of the derivative, right? Because this thing that we start with is dv dt. Taking a look at its derivative is looking at the concavity of the velocity. This is my t versus v graph. And if you wanted to, you could throw in some numbers and take a look at a DE solve, or excuse me, a DE plot on Maple. You could always put some numbers in for R and K and see what happens. Right? And when you do that, you would see a DE plot that's going to make this kind of a prediction. And by the way, above it, it would be downward curved towards the equilibrium solution as well.
So does this imply that it's going away from the 0?
Going away from the 0.
Because we start at an empty lake, right?
Oh, yeah. So we started with v of 0 equals 0. And so it's increasing the derivative, or excuse me, the rate of change of velocity, dv dt, is positive. It's going up. But the second derivative is negative, which means that it's increasing, but at a decreasing rate, right? The rate of change is slowing down over time. That's what this negative implies in the derivative of the derivative.
Would 0 be in equilibrium in this case? Like, are there two equilibriums here?
Absolutely. If it starts off at, oh, actually, no, in this case, no, it doesn't. The way the equation, the rate, this R, accounts for the fact that even if V starts off at 0, there's still a positive rate.
Oh, that's
right? So the volume is increasing. So that's, when I built this one, I made sure that it has a constant rate. Turns out, just in case you're wondering, for application purposes, the evaporation rate for a lake is not proportional to its volume. It's proportional to, if I remember correctly, the volume to the 2/3 power. So it's not quite proportional to volume. It's proportional to volume to the 2/3, which, by the way, would make this differential equation much harder to solve. It makes
Why
it
isn't
really,
it proportional
really
to the surface area?
well, it kind of is, because it turns out surface area is proportional to volume by a power of 2/3. And so that's where the 2/3 is coming from. So if you want a differential equation that is dv dt in terms of volume, that's where the 2/3 power on the volume comes from. It's surface area. And the constant of proportionality has pi's in it and some other constants that are folded into the geometry of things. Okay, so I'm mindful of the time. Any other questions about this one? Everybody's quiet, so I'm assuming no. I wanted to share with you, I just kind of quickly sketched out my solution for number 7. And number 7, we start off knowing that the rate of change of the amount of units produced is proportional to this thing. Is proportional to means we got to have that constant. And so we can try to find the general solution, but there's going to be a constant here that we don't know. the proportionality constant. Plus, if we solve this thing using a by hand method, we're also going to bring on board a constant due to the integration. So there's actually two unknown constants. And that's where, if you use Maple, you can do a quick desolve and you wind up with something like this. Notice there's still the K in there. So I can't use this equation to make any predictions. And so I need one more, I guess you could call it an initial condition. And so I use the other initial condition, which is n of 5 equals 65. And Maple says, oh, okay, well, K equals this honkin' mess, which is, again, just a constant. And then I can throw that in. Now that I have my general solution and I know what K is equal to, I can make any prediction that I want. I can throw anything in for T and make a prediction. Or I can work backwards and say, what if I know the number is 120? How do I calculate the time? And so the way I do that is I would throw 120 in there for my N of T and then solve for T. And of course, I'm using this as K. I just didn't want to rewrite it everywhere. And if I solve for T, I come up with about 21, little over 21 days. So this is the prediction. This is me saying, after the person's been working there about 21 days, little over 21 days, they should be making 120 units on that day. Right? And by the way, this problem was borrowed from a systems engineer's handbook, where this is actually what they do to calculate productivity for people and machines, frankly, in terms of productivity should follow this particular path. It should follow this equation. Part B is really easy. All I have to do is throw in a T of 20 to come up with that solution. So how do we feel about problem set number 5?
A lot better now.
Yay!
Yeah.
So I hereby grant unto thee a wonderful score for problem set number 5. If you have problems to finish them. You have the video of this, but you were here so you can see it. If you're here in the future, tell me about the flying cars and your solutions. That would be really cool. But you have the ability now to finish this up if you need to finish it up. But what I want to do right now is I'm going to hit stop on the recording, and then I'm going to put you guys back into your groups. But I'm going to give you a link before I do to the document for the group part of the exam. So let me open this. Let me grab the shared link so that you can see the team portion. Copy link, done. I'm going to drop this in the group chat so everybody can see this. So you can click on that link and pull up the group portion of the exam.
Will this be anywhere in JetNet, or do we have to save this link?
I'm going to send it out via email. That way everybody will have access to it. I don't know if I'm going to post it in JetNet for a variety of reasons, but what I want you to do now is I'm going to put you guys back into your team rooms, and you can work for as long as you want on this.